Morning, everyone. Welcome to my session. I'm Xin from eBay, and today I'm going to talk about how we run high-performance workloads at scale with Kubernetes. And you're going to hear lots of best practices and lessons learned for performance and scalability. Here's the agenda. First, I'm going to give a very quick intro on eBay's Kubernetes deployments. After that, I'm going to walk through the way we build and manage Kubernetes clusters with a fleet management system based on Kubernetes CRDs and operators. And after building these clusters, I'm going to talk about control plan performance. How do we turn the control plan to make them, be able to run thousands of nodes with heavy workloads? And eventually, I'm going to touch base on the data plan and user space, basically how we build containers, how we write the pod specs, and how we do performance tuning at different layers to run those workloads. First things first, eBay started Kubernetes since 2015. We run an internal distribution named test.io. And within the past 2 years, we moved lots of workloads from bare metals and VMs into containers. And as of now, we have 50 plus clusters. And we run multiple VPCs for different environments. We have both flat network and overlay network based on OVN. And we have multiple 2,000 plus sized clusters with heavy workloads running on them. And in total, and we are growing like for daily basis, but I just took that like 2 weeks ago that we have 160,000 pods running on about like 24,000 hosts. Most of them are bare metals. We only run bare metals for production. And there are so many different production workloads running on there. They're like web front ends, databases, search engines, and even Hadoop. So we are also running on the edge. We pretty much run on so many edge locations so that we can get closer to the eBay end users. We are doing some sort of edge proxy software load balancer on the edges. And we pretty much handle SSL termination from the edge, and we do some caching. And this is a significant boost for our user experience from Europe and APAC. And we are rapidly growing our footprint on the edge as well. So our goal is to unify eBay's fleet on Kubernetes, and we're trying our best to get there as early as possible. So now after getting some idea on eBay's Kubernetes footprints, you might wonder, how did we get there? And the short answer is we use Kubernetes itself to make it all happen. So as most of you know that Kubernetes is a declarative, API-centric, and portable system. It can be used to do so many different things in different ways. We use it to build our private cloud that runs Kubernetes, and that's our fleet management system. Like any other Kubernetes services, it runs with an API server. We run etcd operator to do some sort of etcd cluster management. And once you have the API server, you pretty much will model your data center. That's the most fun part. So we pretty much model every bit from the data center, from racks to switches, from subnets and even routers. And we pretty much models everything from the infrastructure layer. And we have to pretty much model the software bits. We do a model for operating system. We do OS trees so that it's easily modeled and the whole operating system's footprint is tracked by a commit ID. And then we have compute nodes, that's a provision host, and we use Salt to deploy Kubernetes. So we model Salt master, we automate the part to deploy a Salt master to deploy Kubernetes. And once you have all those models, you have to write a lot of controllers to do things for you. So first is to provision. So you pretty much create compute nodes with Kubernetes. So we support multiple providers. We do OpenStack at the very early stages because eBay used to be a super big OpenStack shop. And we support GCP as well. But in order to scale and write high-performance workloads, we want to do bare metals. And we don't want to have all those OpenStack components. We used to do Ironic, but we see many issues with expanding, especially on RabbitMQs. So we decided, let's do our own bare metal provisioning with easy stuff like Kickstart. We use Kickstart and Foreman, and we write our own bare metal provisioning system. And that's completely based on Kubernetes CRDs, and it's going to call Foreman APIs, do provisioning. It's completely declarative. And it's also acting as a provider for our fleet management system. And then you need to install Saltmaster. We pretty much can install Saltmaster and pull a salt tree from Git based on a commit ID, and then build a Kubernetes cluster. Yeah, of course, you pretty much have to do salt minions as well because you are running salt high states to deploy Kubernetes. So we actually implemented so many similar as Kubernetes implementations like salt deployments and node pools. Those are just like deployments is managing replica sets and pods. And we actually support transactions, schedulers, and rolling updates. We do rolling updates for OS upgrade for Kubernetes releases. And some specific workloads can even plug their workload-specific logic into our rolling update strategy. And we do that for our search engine use cases too. So after introducing those concepts, let's take an architectural view. This is a single AZ's view, and we normally have one fleet management system managing one eBay availability zone to make it self-contained. So this is our AZ control plan, basically. So let's see how it works. So first you have API server, you have controllers. Basically, we pack all those controllers, we call them test master, and we have to pre-create a few objects. So OS image, I'm going to mention that later, but we use OS tree to build our own version of operating system. We leverage RPM OS tree and Project Atomic. And this operating system can be built from spec. This operating system object in our API server contains the OS tree URL, the commit ID for this operating system footprint. And we create something called compute flavors, and it will pretty much cover the way you want to provision your bare metal. So for example, you have 3 disks. You want to pretty much do some LVM, some software RAID, MDADM, and you can all put them into specs, and we are going to automatically generate the kickstart file based on that. So now you have predefined those models. Let's say we have a new racks coming into our data center. So after you rack and roll, you have all the cabling done, and you power them all, right? So all the assets by default gets into a PXE image that net boots and self-registers itself to eBay's CMDB. It pretty much populates all those rack information, asset details like serial numbers and LOM IPs and all kinds of stuff. And that's when our controller, we have an auto discovery controller that kicks in. We call it rack controller. We populate everything based on the unit of rack. And it pretty much creates the switches, the subnets, the racks, and even the routes for the whole infrastructure layer. And once you have those assets sitting there ready to be consumed for our homegrown provisioning system, we are going to create compute nodes. So compute nodes can be provisioned by different providers, just like any other orchestration systems. So I'm just giving an example of how do we do that with our homegrown provisioning system. So once you create compute node, our scheduler will pick an asset, and it's going to create the node in Foreman, and we are going to automatically generate the partitioning templates for the specific node based on the partitioning table you want to do. And then, it's going to interact with Foreman, and we do lots of controllers like IP allocation. We do provisioning, we do DNS, and CMDB registration, all kinds of stuff. And they are working with orders, and they are subscribed to either annotations or finalizers to complete the complex flow of provisioning. Once you have the compute nodes provision, you're going to have, you can deploy your Kubernetes clusters. So we use Salt to deploy Kubernetes. You can just go to Git. We have our Salt state repo to manage Kubernetes. You take a commit ID, you put that into the Salt deployment object, which will pretty much create the Salt master for you. And we are going to run Salt minion on those compute nodes based on their different roles. Some of them are masters, some of them are nodes, and that's how we build a Kubernetes cluster. And there's also those other controllers that we do to do scheduling, transactions, and rolling updates. So I won't go further to the implementation details, but I'm going to have a separate session to deep dive into this in the upcoming Shanghai KubeCon. But to summarize, this is an important piece of running our high-performance fleet because with our fleet management system, we model eBay's data center. We have lots of controllers doing different things, and we pretty much have every bit in Git. What does this mean is that, so if you from the ground up, so you have operating system, we built it with OS tree. And we have it modeled in API server with CRDs. And we use Salt to manage host config as well as building Kubernetes. So the Salt is in Git, and you can get a commit ID and build a cluster. And moving forward, you have like Fleet, so which does provisioning, setting up cluster, lifecycle management, remediation, and those are all CRDs that you check into Git. So which makes us think of like GitOps, which is like a natural choice for us. And then you're gonna have some sort of PR-driven operations and everything to be declarative. This is the beauty of this whole system, and that's what empower us to build consistent Kubernetes clusters across the world, and having the capability to really scale our clusters for high-performance workload. Okay, now we have lots of clusters built out there, but how do they perform? So let's take a quick look at the eBay's Kubernetes control plan config. We run 5 masters, active, and they are making one etcd cluster. And each node is running API server talking to its local etcd. We have, of course, controller manager, scheduler running on the same node, and we're running add-on manager. And all of those control plan bits are managed by Salt because they are static pods. And for the nodes, we are running kubelet and kubeproxy with a lot of daemon sets managing like storage, networking, and monitoring. And this all worked fine. But what if you're running like thousands of nodes of 100,000 pods? You see issues, right? So the typical issues you are seeing is heavy listing and watching. And it maps to different layers. And most critical part is etcd and API server. So you're going to see a lot of high memory usage from the etcd. You have very frequent leader election changes, and you are going to have very slow scheduling as well as delayed controller sync. And of course, API server also is going to suffer, and it's going to have like frequent restarts and crashes. So how do we do performance tuning for this? Most of the work here is done by one of our team members. Her name is Yingnan. And the idea is to use KubeMark to get to know the cluster's limit. You really need to know your limit, right? So KubeMark is a tool, it's an upstream tool that simulates like thousands of nodes, and it might not be able to run your pods, but you can really test your performance of the control plan. And then our test case is simple. We're gonna create and delete like 10,000 pods at the same time and see how it performs. And this is pretty much what we get. So I'm going to talk about it from 2 different layers. First is the server side. So API server and etcd are the most critical part. So first things that we found is that you need to evenly distribute the load to the 5 master nodes that I've been talking about, right? So one issue we found specifically interesting is that some of our heavy controllers, for example, provisioning controllers from test master, it creates one client, and it has a session stickness to one API server. And this kind of controller, if it always like DDoS the API server, you are pretty much lost to one API server and you have a flat ping control plan. So you can solve that from 2 different layers. First is that you do some sort of load balancing from the API server, but this wouldn't solve our issues that I just mentioned. You also need to enhance your clients so that they can do some sort of auto balancing from itself so that it can do like multiple clients, and then it can be smart about talking to API servers. I'm gonna mention more about it later. But next it's etcd. So our practice is that always have dedicated SSDs for etcd so that you have guaranteed IOPS. I think this is rather obvious. But the other one is sometimes you want to split your etcd. Some of the folks yesterday also mentioned like if Ingress service controller is underperforming, you can split that specific piece for service controller. But for us, sometimes we need to split the events outside of the main etcd, and we sometimes do like a separate disk for etcd snapshots because snapshot is also heavy. We want to do backup. Our etcd backup happens, I think, every half an hour, so we always are very concerned about losing data, and the snapshotting also has some impact. So you always want to be careful about etcd. And the next one is, there's just a few configs that most of the folks working with API server will change that. So pretty much you want to upper your limits, and you put in the max requesting flights or max mutating requesting flight. And then you always want to do some sort of rate limiting. So you pretty much don't know, like some controllers is doing some super nasty stuff, and some people are doing like tens of thousands of deployments, and you pretty much don't want them to DDoS your API server. And that's pretty much the server side's turning. And from the client side, it's always about writing good controllers. First example is about the list options and resource versions. So many of you might know that if you put the resource version equals to 0, it gets the API server's cache. But if you put that into nil, it goes into the etcd. So you always want to pretty much avoid directly hitting etcd. For some of the cases really need to do that. Like, for example, controller restarts, you want to reconcile and do stuff like that. You don't want to be behind. But when you are actively running, always avoid that. And use as many informers as possible. This is also like a pretty common, performance concern about writing controllers. When you are able to do informers, don't do listings. And we actually, when we are building our complex fleet management system, we have actually so complex objects, and we have a lot of, API calls and interactions with the API server. So we built some sort of metrics collecting function, very simple. Before you make the API call and after you make the API call, you collect the time you spend. For each API call, you are going against the API server. And of course, you have namespaces and the type of API calls you're getting, like get, listing. So you get an idea of how your controller is doing and how they are performing. So that's very important for you to measure the performance and enhance your performance. So the last part, I'm just quickly go through because that's already fixed in the upstream. So sometimes you have some sort of leftover pods. So they are interminating, some of the hardware failed. And in the earlier versions of Kubernetes, scheduler is using mutex instead of RW mutex. So it's one pod can slow down your whole cluster, but that's fixed later, as I mentioned. So basically, you always need to manage your life cycle of the cluster. So our fleet management also does that. It does remediation, interacting with our break-fix system. We can take down the bad nodes, send them into break-fix, clean up from the Kubernetes clusters, and then remember we had this node pool and deployment concept, and we are going to replace with a spare asset and match it as it is. And add it back into the cluster to complete the story of remediation. So now we are moving to the data plan, because we are mostly done with the control plan. So we are going to talk about how we run those high-performance workloads, some of our best practices. So first thing is you're going to build containers for them. So some obvious principle is that you always try to build the containers as a native container, but sometimes some workloads doesn't like it. So we have a lot of heavy workloads. They still want to run some init system. This is like a classic PID discussion that has been going on for a while. So can you run systemd? The answer is yes, but it's a little bit too much. In order to run systemd inside a container for your pit 1, you need to do some cleanup from your container. You need to mount I think a C group FS as read-only, and then you need to make some temp FS. We do that with mtdir. And okay, now you have it running, but that's it? No, it's actually, we see lots of other issues. Like somebody actually captures some Docker image from a Hadoop server, and they think they can just run it. But later we found out, because this is a heavy, high priority projects, we give them all the permissions we can get, and then, they pretty much limit the system configs. And I'm going to talk about that later. But for this specific case, CentOS 7 has a systemd that has hard-coded 65K ulimit. So any Hadoop jobs that's container spin-off, they cannot reach the 100K limit they want. So we have to pretty much patch it and compile a new systemd and put onto that, or they have to upgrade their container image. The actually alternative is to use some smaller init system like supervisor D, or write your own init system. But with the new features coming up, there is a shared pit namespace, and which allows you to manage those processes, and you have your POS container acting as your pit 1. So maybe you don't even need init system later. The next one is you have to be super careful about the capabilities you give. So it's a security thing, but it's also performance thing, because the same container I just mentioned, imagine that it took from a bare metal host, it run turn D, and it has all those capabilities that you give, and it completely mess up your host. And it's so hard to troubleshoot because from the host, you don't actually see anything. And then the last one I want to mention is the container's resource limit awareness. So for some of the legacy systems, they want to do a lot of things from the containers. They do uptime top, check the memory, and see things around to run some jobs, some scripts. But most of you know that from containers, you see most of the things from the host. Well, of course, you can pass a lot of information to the containers by download APIs, by EMVs, but there's some solution that Canonical has. They use it to manage LXDs. It's called LXCFS. It actually do a custom proc file system that overrides a few things like uptime, memory, and CPU, but it only does CPU set. Well, it's quite obvious. CPU share is hard to simulate and custom into the containers. And then the next one is writing good pod specs. We actually use a lot of download APIs, pod presets, basically a lot of capabilities of Kubernetes to make it easy and make all those pods good Kubernetes citizens. And there are lots of interesting features of Kubernetes where you can do to match whatever you run with OpenStack or VMware. For example, like overcommitment. Everybody wants to do overcommitment from VMware, but in containers, you pretty much has a better way. So you can manage the overcommitment ratio by yourself by declare your burstable pods, like you put on like a request and limit based on a ratio, and then you can tolerate the host's overcommitment by yourself. You make the call. And then there's we run a lot of probs. So readiness prob and liveness prob is a super powerful tool. For example, readiness prob, the typical use case is to enable disable web traffic, and liveness prob, you can do some trick to do some self-triggered restarts. And I just want to quickly go through them, but I do want to mention some performance bits of the pod spec. One thing is for stateless applications. Many of our stateless applications, they want some sort of ephemeral drives. And it seems that the only option right now is to use MTDAR backed by hard drives. Well, it's not a perfect one because you're going to see lots of issues like applications just dump their data into MTDAR. They don't really care. And then you ended up adding size limits into the MTDARs, so as to evict them once they are reaching their limits, right? But the implementation is Kubelet is going to do some sort of DU against that folder like every 20 seconds. And when you have lots of them, you're going to have some performance overhead. So for that, we are actively looking at the upstream CSI inline volume support, not just for the kind of informal support, but also we want to unify our flavors to run, the local storage. Specifically, if you look at and compare stateless applications versus stateful applications, we actually have stateful sets running with high-performance local volumes. If both of them can be backed by the same LVM VG, it's much easier for us to manage. Okay, now we have built the pods. We need to run them at the host runtime. So host runtime performance, most of the bits are from the kernel. We can spend another day talking about the kernel, but basically a few basics we want to make sure that we share. So first is that you want to unify the platform and manage as less kernels as possible. Why is that? You have lots of drivers to certify. You have, if you're managing so many different kernels, like for example, eBay is managing ODM, custom hardwares. We have lots of like GPU use case. Adding kernels, adding a lot of maintenance cost. And now let's say you decide on running one kernel, you're trying to run the latest. So the upcoming 4.19 kernel seems to be very interesting. It brought in a patch for network packet batching. And that should improve network throughput by like over 30%. So we are also looking at it. So the next one for host runtime turning is about CPU and power. So you always want to push your server to the limit when it runs high-performance workloads. So you want to make sure that it's running on the performance mode instead of power-saving mode. So you pretty much flip the P state, and you always want to make sure that there's not any other services of the system, like Canonical has like on-demand that's reverting your changes. And we found it interesting that there's a max C state. We always wanted to set it as 0. But it's not absolutely true that 0 gets you more performance, because you always think about some use cases that's super heavy, and then they need to use a lot of turbo from the CPU. So basically what we found is that setting it to 0 is actually way less performing as setting into the default 9 for max C state when it comes to the turbo use case. And then the memory, there's like very common ones about THP. Like many of the database folks will warn you that THP is kind of buggy, but what we found is we actually get a lot of benefits from THP, especially for our search engine use cases. So it's pretty much like workload specific. You always have to identify by yourself. And I do want to mention about the swap, because swap is one feature that we want to avoid for Kubernetes. One lesson learned is that we have a small noisy daemon set that actually runs on a box that has swap, and it has some sort of memory leak. And once it reaches to over 60%, it actually wakes up the swap, and then kswapd slowed down the whole host. So what we ended up doing is we ended up overriding memory swapness and default it to 0 for everything unless you put a specific annotation. So try to avoid swap, because it kind of messes up with cgroup. And of course, we are going to talk about like IO scheduler, CFQ, or deadline, and I won't go further into that. But one thing we found is we default to CFQ, because we found some issues with deadline when we are doing each city backups, but it's basically your choice. I do want to talk about our storage classes, because we have many layers for storage class. We have hot tiers and standard tiers. We pretty much run local volumes for most of the high-performing ones. And we run our own version now, but we are trying to switch to the upstream dynamic local volume solutions from CSI. And we run standalone cylinders so that we can get the Ceph volume mounted to bare metal without going through the hypervisors and VMs stuff, Nova from OpenStack. And there are lots of system configs. I just want to highlight 2. One is you want to limit your stuff. Like there are lots of heavy workloads. You want to limit the kind of resource they're taking so that the hosts don't get bumped up. And then you want to increase a few things. For example, max map count for Elasticsearch. So you always have to find a balance between some workloads that's overusing, some others are not. But some of the things we are trying to do is, first is the CPU set and NUMA. So this is a feature we want to do. And then block IOC group. Obviously, we want to do some better resource management and isolations. And OS query, as well as we are doing some software-defined storage. Okay. Last part is networking performance. I'm not too much of a networking guy, so I don't have too much details here. But luckily, we don't have too much time left either. So we do RPS and RFS. We set that into the VES devices, and this is super helpful, which gets us to the similar as bare metal throughputs. We do IPVLAN for high-performance workloads. For standard ones, we use OVS and VS. But some search engine workloads, we run IPVLAN. And of course, we are trying kubeproxy with IPVS mode. And there's a BBR that we are using for search engines and like our edge computing. So BBR is good for consistent rates. So consider it if you have such kind of use case. And then the last one is the TCP configs. We do some like traffic controls, FQ cutoffs, and TCP slow starts. So I won't go further into that because we don't have enough time left. But we do want to do IPVLAN and eBPF. And we are actively thinking about the solutions to network QoS. The last part is sometimes you want to isolate your workloads. You see so many different configs that I just mentioned. You profile them and you want to isolate them. So how do you do that? So stopping one workload to step into each other, you pretty much can do like no schedule. You do with tense and tolerations, but there's no schedule and no execution. So what we found is that no execution is actually too aggressive. It actually evicts some of the no selecting pods, which we actively use for like volume recycle. So you don't want to go with no execute, we do no schedule. And you always want to monitor your performance. There's a lots of tools I listed here, and there you need to do a lot of benchmarking and burning tests, and more importantly, if you can automate that part, we actually are actively working on integrating all those performance bits for specific use cases into our OS image CI/CD as well as our certification flow for new hardware. So that's pretty much it. Lots of contents. I might have run a little bit too rush for some of the stuffs. If you miss anything, you can find the slides online. I'm not sure how much time we have for Q&A, but time is yours. Thank you.
Yeah, we have like 3 minutes. We only have one microphone, so if anyone does have a question, shout it out, or I can run to you and then run back. One right at the back. You want to try shouting? Oh. Where's the question? There.
Hey, a really good presentation. I want to ask, like, how do you manage your to upgrade your Kubernetes clusters, and how that does interfere with the applications that you have installed on Kubernetes?
Do not say repeat the question.
Actually, I didn't.
Just. You're going to have to ask him in the hallway because he didn't hear the question. I think we're out of time now. Thank you very much.
Yeah, I'm here. So, yeah, if you can find me from the hallway for any questions.